My name is Andres Erazo, Chair of the Robotics and Automation Society of IEEE Ecuador. I'm going to be your host at this webinar today. I hope you are all well passionate about deep learning, because in this webinar we're going to talk about deep learning processor architecture, the scaling from computer arithmetic point of view, also multiple mixed precision and flexible precision techniques, which are newly introduced, and some benefits from deep learning neural networks, which will be demonstrated. Moreover, deep learning applications will be introduced, including CT engine, ultrasound imaging, fast detection of explosives, license plate localization recognition, and FPGA-based advanced hearing aid using deep learning. To begin, may I present you to our IEEE senior member, Ph.D. Seok.Bum Ko, from the University of Saskatchewan, Canada. Professor Ko belongs to the Department of Electrical and Computer Engineering in the Division of Biomedical Engineering. His research activities include 40 journals and 66 conference publications with 4 patents and many research grants and awards. I request the audience to mute your microphones to avoid interruption. The exposition will last approximately 30 minutes. If you have questions, they will be answered at the end of the presentation. Professor Ko, welcome and thank you for accepting our invitation. You may proceed with your exposition.
Okay, thank you very much for your warm Professor Uraja. Can I have 30 minutes? Am I correct?
Yes, you are correct. 30 minutes.
Okay. Yeah, all right. So, hello everyone. My name is Seok.Bum Ko from Electrical and Computer Engineering Department and also Division of Biomedical Engineering, University of Saskatchewan, Canada. I'm very pleased to share some of my recent research topics with you today. The title of the talk is Deep Learning Processor Architecture and its Applications. Now, this slide shows the contents of the talk. My talk consists of 2 parts mainly. The first one is hardware design for deep learning, and I'm going to introduce some of the examples using deep learning techniques in the second part. Right? So let me begin with the multiple precision fused multiply add unit. As you can see, if you major in electrical and computer engineering, FIL filter is quite popular, and as you can see, A times B plus C is the most popular computer arithmetic. At the bottom left, you can see deep neural network. Y is equal to W, which is weight, times X is input, plus B is bias. So again, this is very similar type of A, B, or C. It was a basic computing unit in many old days as central processing units and GPUs. This slide shows the main difference among CPU, GPU, and TPU. So the second one is GPU. The main difference between CPU and GPU is you can see the area of arithmetic logic unit, because GPU is a very specialized arithmetic unit processing. The TPU has the matrix multiply unit and accumulator. IEEE 754 2008 standard defined the floating point format, single precision. In the block diagram, sign bit 1 bit, 8-bit mantissa, and 23-bit 8-bit exponent and 23-bit mantissa, in total 32 bits, double precision, quadruple precision. But recent ENN applications, many people realize that half a precision, which is 16-bit, might be big enough, or even 8-bit, even smaller bit would be good enough. So my main idea of this multiple precision fused multiply add unit is to include the half precision into the single precision, double precision, and quadruple precision into a single chip. So if we include the half precision, it's going to be faster, and it'll use a smaller streets, and obviously it's good for deep learning and linear algebra acceleration. So the support of mixed precision operation looks like in a block diagram. On your right side, you can see p-bit multiplication and the qubit addition are mixed together. So I call that this is a mixed precision dot product. So this is the proposed unit. This is the full pipeline with 4 stages, and we're going to use a mode, half precision HP, single precision SP, double precision DP, quadruple precision QP. The mixed is a normal or mixed precision. And this proposed unit can cover a lot of different FMA operations. Now, one big question is, if we include all operations into single chip, we may lose the performance. That's not the case. One quadruple, 128-bit FMA can be accommodated into this chip. If the double precision is required, then our proposed unit can cover 2 parallel double precision FMA. Similarly, 4 parallel single precision FMA, 8 parallel half precision FMA. So, the throughput-wise, we don't lose any throughput performance at all. Whereas we can still cover quadruple double precision and the single and half precision. So this graph shows the area comparison with the standalone design. Only 6.5% more area to support the mixed precision operation. This chart shows the green one, the bottom proposed one. It shows the what kind of operation that we can cover. Okay, and this work has been accepted to IEEE transaction discipline. That's the first multiple precision FMA unit. And the second one is the flexible precision multiply and accumulate unit. If you see the block diagram, the diagram at the below, standard floating point 32-bit, 8-bit, and 23-bit. This is pretty much fixed. And my idea is exponent can be expanded. Let's say 8 to 10 bits, then Mentisa bit will be reduced from 23 to 21 bit accordingly. So if it's a dynamic range, even if we use a floating point 32-bit, then it can cover more range. So that's the whole idea of the flexible precision multiplier unit. So this graph shows the justification of why we need a flexible precision MAC unit. The left side shows the SkipNet, the AlexNet, GoogleNet, BDD16, some of the deep neural network. As you can see, number of bits in exponent in x-axis, 0, 1, 2, compared to 3, it shows the big difference in terms of accuracy, which is in y-axis. However, number of bits in Mentisa, you don't see any meaningful difference between 1 to 5 Mentisa bits. So we can have more dynamic range in exponent by using flexible precision multiply accumulate units. And also this one has a variety in precision requirements, different neural networks, and various layers. So for inference, we can cover this 5 floating point, fixed point, and ternary binary neural network. And also multiple precision computing, floating point, fixed point can be covered. As I mentioned before, range first, which is exponent, and then precision, the Mentisa part. And this fused arithmetic unit is equivalent to dot product operation. This one shows the proposed flexible precision MAC unit. Again, right side shows the supporting operation and the flexible precision computing. So this is how we implement the flexible precision unit using masking. And this one shows the comparison with the standard arithmetic units. So as you can see, this one shows a lot less area than floating point 32-bit, and also a lot lower power consumption. did two case studies. One is for an edge device, which is a little light deep neural network. We compare with the fixed point 8-bit unit in LUNET. LUNET contains a fixed 3-bit, fixed 5-bit, and fixed 8-bit. So if you use a standard fixed point 8-bit unit, you don't have any other alternative. But our proposed flexible unit can handle 3-bit, 5-bit, and 8-bit accordingly. So as you can see, compared to relative accuracy to 40.32-bit, accuracy is 98% for both. And power-wise, as you can see, fixed point 8-bit unit has 1.17 milliwatts, whereas our proposed flexible unit has 1.05. And the second case study is a server data center side, LUNET, AlexNet, and GoogleNet. It contains a fixed 7, 9, and 10-bit. So our proposed flexible unit can dramatically reduce the power consumption compared to 10-bit. This paper is on the second video of IEEE computer, and this one has a lot of interest from the reviewers. So my final goal is to build all the CNN accelerator into a PGA. In this block diagram, MAC unit, that's the processing element. So all the IP that I just introduced today, it's going to be implemented into that MAC unit. So this is a detailed internal structure. And we're going to use a traditional computation reordering and loop unrolling, those type of things. And typical convolution 3x3 kernel with stride 1 and 2, and also 1x1 kernel have also been implemented. This is the preliminary result. We implemented the YOLO version 3 into Intel Area 10 SoC development kit. Power is around 30 watts. My next plan is to apply the proposed flexible MAC unit into this FPGA-based CNN accelerator. The next one is approximate computing. Just to look at the underlying part, altering the architecture such that there is a reduction in accuracy in exchange for low power consumption, area usage, and delay. So by maintaining a acceptable accuracy or performance, then we can dramatically reduce the power consumption. Especially in cell phone era, this is one of the key techniques for deep neural network research. So this one shows the approximate boost multiplier. The left side is the original, right side is our proposed. As you can see, number of gates are reduced. This one we proposed 3 different multipliers, and the second one shows the half of the power just is required compared to the exact multiplier, 41% in multiplier 3 and 50% in multiplier 1. This one is also in the second video of IEEE transactions and computers. Also, we expanded the idea to divider from A to B. The B is much simplified version of A. And this block diagram shows vertical blue line. Left side shows the exact cell. We didn't touch the exact cell, but the right side we replaced the exact cell with our own approximate cell. So we were able to get the power consumption reduction by up to 46%. This is we present this work in the discuss this year, and the extended version is also under review at the IEEE transactions and computing. This is approximate MAC unit, which will be very useful and powerful for deep neural network operation. So this one also can improve area power product by up to 66%. This one also has been presented into ISCAS this year. RISC-V also a good topic for deep neural network processor architecture, which is open source and license-free architecture. What I'm focusing on is, as you can see from the left side of the 32-bit standard status, the part is pretty much fixed, but packed SIM, the vector transactional memory that is open, so that we can generate the specialized instruction sets. So scale of pipeline design and dynamic pipeline designs. And these are the topics that I'm thinking of to explore, the extension to compute the 2D convolution. And the next one is how we integrate the original core and the external convolution engine. Simple way to accelerate the deep neural network. This one shows, look at the method 1. The yellow box shows the numbers, and F0, the light blue one, shows the matrix multiplication. Now you gotta calculate all the calculation to get the -13. But if you reorder the number, at some point, like just to try to multiply positive number first, and if you get the negative number, then you don't have to continue the remaining things because it's gonna be negative anyway. So by avoiding unnecessary computations, that we can certainly decrease the computation time and reduce the power consumption significantly. So we also have other methodology using winograd algorithm method 2 and enhancing winograd algorithm and the enhanced version of method 1. So the bottom part shows the power reduction and speed up compared to the original one, and as you can see, about 10 to 17-18% power reduction for both AlexNet and BDD16, and speed up wise, let's see, 1.8 to 2.6, 3 times the speed up has been obtained. The last one of the first part of my talk is stick-based deep neural network accelerator. So this is a USB type. By putting this one, the inference for generated deep neural network models to be run in situ and in real time. So nowadays the drone is pretty popular, so we can use this one into drone so that it can generate the output right away using some of the communication channel. Now this is the second part of some examples using deep learning. The first one is long model classification for computed tomography, which is CT scan. You see two images. The left one shows the benign nodule, and the right one shows the malignant nodule, which is cancer. And as you can see, it's difficult to classify which one is cancer because of similar visual representation. We developed the deep neural network using this block diagram A and B, and eventually we compare with the original AlexNet, and as you can see, significant processing time improvements compared to the original one. This is accepted elsewhere academic radiology. This is an interesting slide. Student 1, student 2, these are medical students, relatively less experienced radiologists. And the right side, the thoracic radiologist 1 and 2, this is about 20 years experienced expert on that side. The blue graph shows their own classification, and the red one, before red one, we show the AI results to the participants, and they have a chance to change their mind or to revisit their own things, and the y-axis shows the accuracy. In particular, inexperienced radiologists, as you can see, the accuracy has been dramatically improved from blue to red. So this is evidence that our AI model, or deep learning model, at least can be used as a second review or supplemental tool to the radiologist. And this is more complicated deep neural network architecture. We improved the long nodule classification on CT by proposing multi-path feature extraction, which is A, and the C, multi-scale convolution layer. Basically, we try to get more features and contour of the nodule or unique pattern structures, or by combining 3 different filters so that we can have a better classification of the results. So this is the result. And the second one is breast lesion classification of automated breast ultrasound. Ultrasound is preferred by the patient. However, it takes a significantly longer time and the resolution is not that great. So it's not preferred by the radiologist. So our task was to improve the classification of ABUS, automated breast ultrasound. So we developed the Inception version 3 based model like this, and also we modify the structure using multi-view strategy A and B, again based on the Inception version 3. So this one shows the result, the sensitivity, specificity, and as you can see, our AUC is the best. Okay, this one is about bone. Ankylosing spondylitis (AS) is an symptom or disease. It takes 7 to 10 years to be fully developed, but it's difficult to diagnose at an early stage. So, using some machine learning technique and deep learning technique, again based on Inception version 3 as a backbone, we were able to get the very high accuracy for this proposal. Okay, and that's the second example. Rib tracking labeling classification system is also interesting because if you look at the emergency room setup, not always you have a radiologist in the room. Now, if you have a patient that has some rib fracture, it's very tedious and difficult to say which rib has what kind of rib fracture. So we developed our system. If you look at the stage 5 at the bottom, we use a deep neural network to classify the rib fracture. So this one shows some of the image processing pipeline, and this one also is based on the Inception version 3. Let me see if you can see the video. So from this video, the red bounding box is acute, and blue is old one, green is regular. That's what the radiologists want to see. So our system was perfectly able to classify all the things in a very short time. Total processing time was only 51.48 seconds. The next one is we also apply the deep neural network to electronic nose, like combining TNT or gunpowder with either soap or toothpaste. This one also brought some interesting phenomena. We tested the SVM, support vector machine, and CNN and LSTM. Now, x-axis shows the time length of the data. The overall performance is pretty much similar, but one interesting point is that the LSTM model, which is a green graph, needs just around 50 seconds of the training the data to provide the acceptable accuracy, which is above 85%. Whereas the other CNN model needs around 130 seconds, and the SVM also pretty much same time. So with the very short time data, which is around 55 seconds, LSTM shows the best results. So that's the second one. Now we also apply the license plate localization and recognition using a mobile net-like architecture, which is modified SSD object detection deep learning model. And this is stepwise the separable convolution that we use mainly to reduce the computational complexity. So as you can see, our developed deep neural network system shows the best results in terms of correct detection and processing time as well per image. This one also shows some video. We used a very low-cost embedded system, Raspberry Pi, and using cell phone. The video stream is fitted to the system, and as you can see, this one was taken from the Saska too. You see all the license plate dots has been recognized with the green rectangular box. Let me stop. Okay. This one, you can clearly see the license plate has been recognized with the green rectangular box. And also, it can be easily extended to the recognition. Recognition is just OTR. As long as our deep learning model can extract the license plate, and then the recognition is a much simpler methodology. So ours, compared to other techniques, shows the better recognition accuracy. This is probably the last one. Shows the FPGA-based advanced hearing aid using deep learning. The core part is FFT. As I mentioned before, our lab has a good number of arithmetic IP cores, including FFT, and also we are planning to apply deep neural network to remove the noise for hearing aid. As you can see, right after FFT, we put RNN and LSTM to remove the noise before it sent to network interface. So this is all that I prepared today, and this is my lab members' picture. And I would also like to acknowledge all the sponsors for my research, starting from IRD, Xilinx, GIPS, NSERC, Yovas, Intel, NVIDIA, and Microchip. Okay, I'm done, Professor Gallardo.
Thank you very much, Professor Ko. We still have time for one or two questions. Maybe the audience have some questions. Please let me know so that I could mute you. Okay. I think we do not have questions. I have one. You have tried these neural networks on a linear and parallel type of processing controllers. How is the performance in each one of them?
Can you repeat your question again?
My question was, have you tried these networks on sequential and parallel processing microcontrollers? And how is the performance?
What do you mean by your model?
I mean like FPGAs or...
This FPGA is specifically for deep neural network acceleration.
Okay.
Not just a typical like a sequential or parallel application of traditional application.
Okay, so the performance is improved.
Performance of compared to the traditional deep neural network, obviously because it is specialized, having some of the proposed technique that I mentioned are integrated into this one. So obviously, I'm expecting that our performance will be better, but that one has not been integrated into FPGA accelerator yet. We just built the reference model, which is regular. Now we have a chance to replace the regular model with our IP, because if you use a other technique, then you don't have any control over their work, right? It's almost impossible to replace their component. So to answer to your question, I'm 100% sure our accelerator will be much better, but we haven't tried that part yet. We just built the reference model into Intel oriented SoC board.
Okay, thank you, Professor. Maybe any other questions from the participants? You just have to write in the chat so I could enable your microphone. Okay. Christian has a question. I'm going to enable his microphone now. Okay, Christian, we can hear you.
Okay, I just got one question. Your process seems to detect like the development of cancer, but what I don't understand is how does the data acquisition? It does in just one period of time, or it is continuously done to the patient?
Can you narrow down the application? Let's say, how about lung nodule, lung cancer detection, right?
Yeah.
So your question is, how do I get the data?
No. My question is how your application detects the development of cancer, because I saw in the graphics that it acquires the data continuously.
Continuously means, let's say we developed the model, right? So the software is available. Now the patient is coming to the hospital. They will take the CT scan. So that CT scan will be the input of our developed model, and our model will tell this patient has a cancer or not. So that's the whole idea.
Okay. So it can help to detect the cancer fastly.
Yeah, exactly, and also more accurately. As you can see, the deep neural network model shows the even better performance than experienced radiologist.
Yes, I noticed that, but it means like that your model is able to learn the patterns of the cells developing cancer.
Right.
Okay.
So, hopefully, if the patient comes to the hospital at a very early stage, and you can recognize it right away.
Okay, thank you.
In case the radiologist was not able to tell this one has a cancer or not, but hopefully AI can detect the cancer images.
Okay,
thank you.
All right.
Okay, thank you, Christian, for your question. But I think we have for one more question. If somebody want to ask another one? Okay. It seems not. We gave our special thanks to our expositor, Professor Ko, to share his knowledge and support with our community. We hope we could have you at a future webinar anytime soon.
Okay. Okay, thank you very much for having me.
Okay. I'm sorry, if you have any other question, you can send them to my email. I'm going to put it on the chat so that I could forward them to Professor Ko. Also, thanks to all participants for attending. We got an audience of approximately 40 people on our first RAS webinar of the year. Don't forget to become RAS members. Tell you about our next webinar to share another piece of interesting topics of automation and robotics. Thank you, everybody. Bye and take care.